Hello again. In the last video, we looked at matrix notation and we saw how to put a system of equations into a matrix. This first matrix here is called a coefficient matrix because it consists of just the coefficients of the system of equations here in number 3. Number 4, on the other hand, is called a augmented matrix because it adds a fourth column here of numbers 0, 8, and 10 on the right side of the equal sign. This augmented matrix is a 3x4 matrix. It's called a 3x4 since it has 3 rows and 4 columns. The first number here is always represented by the rows, whereas the coefficient matrix is a 3x3. In this video, we're going to see how to solve this system using the augmented matrix. And we're going to look at the work that we did on our last video. Example 1. So let's go ahead and do example 1 again using our augmented matrix. To solve this using matrices, I'm going to use the same process as I did on the last video, example 1, using elimination. And if you remember, I got rid of the 5 in this third equation. Took -5 times equation 1, added to equation 3 to get a new equation. So I'm going to do the same process here. Our goal is to get a triangle of zeros. We already have a 0 there, but we need to get this triangle of zeros when we solve a 3x4. So what I'm going to do is I'm going to take -5 times row 1. I'm going to add it to row 3, and I'm going to replace row 3 by that new addition, just like we did when we used elimination. -5 times equation 1 added to equation 3. Well, now it's just row 1 and row 3. So let's go ahead and do that. Row 1 and row 2 are going to stay the same. The only thing that's going to change is row 3. I'm going to put a little -5 here to help me out. So we're going to have -5 here times this entry 1, and I'm going to add it to 5 to get my 0. If I do the next one, -5 times -2 is 10, added to 0 is 10. If you want to see how I did that, I took -5 times 1, added to 5, that's how I got my 0. And this one I took -5 times the -2, added to 0 to get the 10. The next one, -5 times 1. -5 times 1 is -5, added to the -5 here is -10. And continuing on, -5 times 0 is 0, added to 10 is 10. And you can see here we get a new third row, which, by the way, is equivalent to the 3 equations here now if you put it back into matrix form. Back into a system of equations. So we use this 1. We're going to, in the next section, they're going to call 1 a pivot to find those 2 zeros. If this wasn't a 0, I would do that one as well. And I always do that first. Then I'm going to come here on my second column and get the zeros, and I'm going to use this as my pivot. That is the number I'm going to use to get a 0 down below, which you can see it is the same term that we used on the left here in the elimination method to get the 0 in this third equation. And to get that 0 here, we took -5 times row 2, added to row 3, and again put into row 3. So let's go ahead and do it. Again, the first 2 rows do not change. And the third row, we'll put a -5 now on this, will become -5 times 0 added to 0 is 0. That does not change. That's good. -5 times 2 is -10 added to 10 is 0. -5 times -8 is 40. Added to -10 here is 30. And finally, -5 times 8, -40, added to 10 is negative 30. And you can see here, that's exactly what we got. We look at our three equations now. It's exactly what we got here on the left. We can stop here now and go for back substitution because we got our triangle worth of zeros. We can start with the third equation. Looking on the left here, we can solve it exactly what we did. Divide by 30, we get the negative 1. Going back and looking at equation 2, this is the equation for the second row of the matrix. Plugging in a negative 1, we get the x2. And finally, plugging in for the first equation, let me make that smaller. We can plug in both the negative 1 and the 0, and we get the same answer. But I'm going to do something slightly different just to show you another method for this. This sometimes in the next section is called echelon form, but we can get something called reduced echelon form. Well, how you get reduced echelon form is you need a diagonal worth of 1s. So let's go ahead and do that. I'm just going to take that second row and multiply 1/2 or divide by 2. I'm not going to change my first row, and my second row will now be 0 dividing by 2, 1 or multiplying by 1/2, negative 4, and the last one here is 4. And you can see we could have done that on the left here on the second equation at any time. It doesn't change the solution. So I'm going to do the same thing with my third row. I'm going to multiply by 1/30. Or if you'd rather just think of it dividing by 30, that would be fine as well. We get 0, 0, 1, and negative 1. And then what I'm going to do is try to get a upper triangle of zeros, which I've marked in yellow. Now I'm going to go backwards, and we need to get the third column first. I'm going to use this as my pivot. This 1 here in the third column is my pivot, and I'm going to get it 0. So I'm going to take 4 times row 3, added to row 2, and put into row 2. The only thing that changes here is row 2. I'm going to write a little 4 here to help me out. So notice how if I take 4 times 0, add it to 0 here, it does not change. That's first entry. 4 times 0 added to 1 does not change the second entry. But the third entry now in the second row is going to be 0. 4 times 1 added to negative 4. And 4 times negative 1 for the last entry added to 4 is also happens to be a 0. Now we can rewrite the first equation, but I'm going to go ahead and do both of these at the same time. So now I'm going to get a 0 in the third column, first row. And again, I'm going to use this as my pivot. So I'm going to take negative 1 times row 3, add it to row 1, and replace it by row 1. So then I'm going to erase this 4, maybe make this a negative 1. And you can see here that this is going to be my new row. So let's just look at that. Negative 1 times 0 does not change. It's still a 1. Negative 1 times 0 added to negative 2 is still a negative 2. Negative 1 times 1, though, is added to 1 is 0. That's what we're looking for. And finally, the first row, last column, is negative 1 times negative 1, which is a 1, added to 0, which is a 1. So that's how I got a 1 there. So we still need to get a 0 in this first row, second column. What I'm going to do to get that is use my diagonals as a pivot. That's the pivot I'm going to use. I'm going to take 2 times row 2, added to row 1, and I'm going to replace row 1. The only thing that changes is row 1, so I rewrote the last 2, and I put a little 2 here to help us. So 2 times 0, which is 0, added to 1, does not change, it's still a 1. 2 times 2, added to negative 2 is a 0, that's good. The next one doesn't change because 2 times 0 is 0, added to 0 is 0. And then finally, 2 times 0 added to 1 is 1. The benefit of getting it in this, what we call reduced echelon form, which we'll see in the next section, that is where you have the triangle, lower triangle of zeros and the upper triangle of zeros with the ones and the diagonal, is that now the solution is visual, as you can see on the left. This represents x1, this represents x2, this represents x3, and if we put it back into a system of equations, the first row says x1 equals 1, the second one says x2 is 0, and the third row says x3 is negative 1, which is indeed our solution on the left. So let's look at one more example. But before we do, let's go over our elementary row operations. So these are the 3 rules that you can use without changing the solution to the system. One is the one we kept on doing over and over again. Replace one row by the sum of itself and a multiple of another row. Another paraphrase of this is add to one row a multiple of another row. We can also interchange 2 rows. We haven't done that yet, but we'll see it here. And you can see if you interchange these 2 rows or any 2 rows, it's not going to change the solution to the system. So that is obvious. And then multiply all entries in a row by a non-zero constant. We saw that up above. If I divide or multiply everything through by the same number on both sides, it shouldn't change the solution as well. So let's go ahead and do this one. So first I'm going to put it in matrix form. So my first column would be 0, 2, and 4. My second column would be 1, negative 3, negative 8. My third column would be negative 4, 2, and 12. I'm going to do an augmented matrix, and finally I'm going to have my fourth column to be 8, 1, and 1. If you think of reduced echelon form, where you need a 1 here eventually, you need to use this as a pivot. You can't do that with a 0 there. So this is when you would interchange 2 rows. So I'm going to interchange row 1 and row 2. And if I interchange these 2 rows, I get the first row to be 2, negative 3, 2, 1. The second row to be 0, 1, negative 4, and 8. And then that third row does not change. So now I can multiply the first row by negative 2. And I can add it to the third row to go into the third row. Using now this is my pivot. My first 2 rows do not change. I'll put a negative here to help me. And then let's go ahead and do it. Negative 4 plus 4 is 0. Negative 2 times negative 3, 6 plus negative 8, negative 2. Negative 2 with a 2 is a negative 4 plus the 12 is an 8. And finally, negative 2 times 1 is negative 2. Added to 1 is a negative 1. So once I get these 2 zeros, I'm going to use this as my pivot and get a 0 down below. So I'm going to take 2 times row 2, add it to row 3, and put into row 3 to get, put in a 2 there, I get 2 here, I get 0, I get another 0 here. Negative 8 plus 8 is 0. And then finally, we have 16 plus a negative 1 is a 15. There's a problem here. If you look at the last row, if you put this back into a system, just that last row, you would get 0x3 equals 15. That just doesn't make sense. This means 0 equals 15. That doesn't work. So this is that case that we saw in the first video where it's inconsistent. There is no solution. Inconsistent. In fact, if you look at the question, it says determine if the following system is consistent. So the answer is no, it's not, because it's inconsistent. And here's what the picture looks like. Here's a graph of the 3 equations. If you remember from the first video, each equation is a plane. And as you can see here, there is no point where all 3 of these equations intersect. Right? This, for instance, there's a line here between the pink and the green or yellow that has solutions here, but it doesn't intersect with the blue. It doesn't have to look like this. It could be 3 parallel planes. There's all kinds of different scenarios.